Today, last portion of the chapter, actinides. Actinides are F block elements in which electron filling is in 5f orbital. Actinium, thorium, protactinium, uranium, neptunium, plutonium, americium, curium, berkelium, californium, einsteinium, fermium, mendelevium, nobelium, and lawrencium. These elements are radioactive elements. And up to uranium naturally occurring, but after uranium they are synthesized in the laboratory, therefore they are known as transuranium elements. But also you can see the cases of oxidation state. +3 is common in all, but in the case of actinium, +3 has extra stability due to 0 configuration, and in the case of curium, +3 has stability due to F7 configuration, and in lawrencium, +3 has stability due to F14 configuration. But M4 plus is stable in the case of thorium due to F0 configuration, and in the case of berkelium due to F7 configuration. And here, higher oxidation states are also possible. In the case of lanthanides, we mainly identified the oxidation states as +2, +3, +4. And here +7 oxidation states are also possible. Now we can see some of the important properties of actinides. The actinides or actinoids are radioactive element I already mentioned, and their half-life periods are comparatively higher half-life period for the first members, earlier members, and the half-life period decreases as we move to transuranium elements because they are synthesized and stable, and their half-life periods ranges from, you can see, a day to 3 minutes. And in the case of actinides also, there is a gradual decrease in the size as we move from actinium to lawrencium. And that gradual decrease in size is known as actinide contraction, like a lanthanoid contraction. The actinoids show in general +3 oxidation state. You have to remember it. Like lanthanoids, actinoids also show general +3 oxidation state. The elements in the first half of the series frequently exhibit higher oxidation states. For example, the maximum oxidation state increases from +4 in thorium-2, +5, +6, and +7 respectively. Higher oxidation states are also possible. The magnetic properties of the actinoids are more complex than those of the lanthanoids. Complex magnetic properties. Now we can see some of the uses of applications of D and F block elements. Iron and steel are the most important construction materials. All of you know it. Titanium oxide for the pigment industry and MnO2 for use in dry battery cells, along with the carbon electrode manganese dioxide is using. Battery industry also requires zinc and nickel or cadmium. You may have heard about nickel cadmium cells. Mercury also required in battery industry. UK copper coins are copper coated steel. The silver UK coins are a copper nickel alloy. In the name copper coins there is copper, but actually it is copper coated steel. But in silver UK coins, That is an alloy, copper nickel alloy, there is no silver. Catalyst, an example, Ziegler-Natta catalyst. TiCl4 with AlCH3 thrice. That is Ziegler-Natta catalyst used in the manufacture of polyethylene. Only a few examples that you have to remember. If some applications are asked, you can write it. Now see some questions. Name a member of the lanthanide series which is well known to exhibit +4 oxidation state. Cerium is an example. Because in +4 state it will get a F0 configuration, 4F0 configuration. Another question, actinoid contraction is greater from element to element than lanthanide contraction. Why? Because of the 5 of low shielding effect of 5 of electron. Poor shielding by 5 of electron in the actinoids and that by 4 of electrons in the lanthanoids. Okay, this chapter is over and we can stop this discussion here.